Good evening, this is Professor Francis, and I would like to go over some of the material that we were studying this past week. Okay, so in section 3.2, we talked about some of Newton's greatest accomplishment, his great synthesis, right? We're going to use Newton's second law in this examination or in this exercise. And also, I want to mention in section 3.3, we talked about something else that Newton did, which was Newton's universal law of gravity. Right? So let's just take a look at that, take a closer look and see what those two imply, and also if we can deduce any other known quantities that exist. Right. So for example, let's say if we wanted to calculate the acceleration of gravity on Earth or some other planet or moon, right, we can use these two formulas or these two explanations of how laws of nature work, and we can find or derive an equation for gravity, a general equation for gravity, and then apply it to two different planets and see if we got it correct. So let's go ahead and do that. First, let's go over what the parameters are with Newton's universal law of gravity. Okay, so that was covered in section 3.3. Let me make this a little bit bigger for you so you can see. So you see the new universal law of gravity says the force of gravity equals G, which is a gravitational constant, times the product of the two masses. So mass M1 and M2 divided by the distance between them, R2. Now, if we look at this slightly different, we can actually apply this to, you know, slightly different scenarios. Let's say M1, all right, here let's designate M1 as a mass of a planet or a moon, right? So M1 is going to be the mass of planet and moon. And M2 is going to be M2 is the mass of something much smaller that's on the surface of the planet. It can be an object or a person, but obviously a person is much smaller than a planet or moon. So it's a very much smaller. So what would R be? R is going to be, here we have R squared. Let me just put that in there. Use a little caret to indicate that it's squared. So R is going to be the distance between the person, M2, and the center of gravity, or the center of the I shouldn't say center of gravity, it's a little off, but the center of the planet or moon. Okay. So given that, we only need to know the radius of the planet that the person or object is on, and we can calculate, and the masses, given the gravitational constant, we can calculate the force between them, right? Now we're going to do something a little different. We want to know what is the acceleration of gravity for, let's say, any object or person on the moon, right? So we had to use these formulas on how to figure out the acceleration of gravity, right? And what's going to help us do that is Newton's second law. Remember what he said, and remember what Newton's second law was. If we come over here and take a look, it says this Newton's second law is a change of motion. It states that the change of motion of a body is proportional to and in the direction of the force acting on it. So mathematically, where F is the force, right? M2 would be the person, and G would be the acceleration. So we have F equals ma. That is Newton's second law put in equation format, right? But look at this. F equals ma. F is a force, right? Force equals mass times acceleration. So this is a formula for force, m times g. And over here, we have a formula for force involving the gravitational constant, g times the product of the masses divided by the distance between them. But they both are forces. And if we're talking about the same objects, we can equate these. So let's go ahead and do that. And remember, the purpose of this is we want to find out what this acceleration g is. So hold on a second. So here we have our two formulas for force, right? Remember, M2 is the object is much smaller than M1. M2 is the object or person that's standing on the surface of the planet, right? G is the acceleration, but it's equal to that force. These forces are the same forces we're talking about. Over here, we have another formula for force, the same force, where G is a gravitational constant, M1 times M2, those are the two masses. M1 would be the mass of the planet or moon, M2 would be the person, and R is the distance between them. Now, what we can do is since they both represent the force, the same force, we can equate them to each other. So we're going to say mg2, m2g this mass times g, the acceleration, equals g, capital G, the gravitational constant times the product of the forces divided by the distance between them, right? If we realize we have m2 on both sides, so this m2 is the same mass. So that cancels out, right? Divide this side, the left side by m2, divide the right side by m2. What do we end up with? We end up with an equation that has the acceleration of gravity on one side, right? And only one mass on the other, the mass of the planet, right? So the acceleration of gravity equals the gravitational constant times the mass of the planet or moon divided by the distance between the person on the surface and the center of the planet, right? So basically, that's the radius divided by the radius of the planet or moon, right? So what does it mean we don't that now that we don't have that mass of the person there? What does that mean? Does that mean that the acceleration of gravity is not dependent on the mass of that person? Yes, absolutely. So it doesn't matter the mass of the person or object on the surface of a planet, right? You're still going to get the same acceleration of gravity for every object. And isn't that what Newton stated? Well, he stated, we didn't cover that, but that was one of the things that he stated. He stated that everything falls to Earth at the same acceleration, right? That's what that acceleration means. That's what this formula here, F equals ma, a acceleration. In this case, we're going to designate g for the acceleration of gravity. So g is the acceleration. So everything that falls on Earth experiences the same acceleration, right? The same value of the acceleration. So let's go ahead and calculate what that value is. And it's independent of whatever the mass of the object is. That's the thing that you can uh, draw from this final equation. There's no M2 here. Remember, M2 is a person or object that was on the surface. There's no M2 here. So it's always going to be the same value. The mass of the planet doesn't change. The radius of the planet doesn't change. If the object or person is standing on the surface of the planet, they're going to experience the same acceleration regardless of their mass. All right. So let's go ahead and test. Now, we already know the acceleration of gravity on Earth is 9.81. But let's go ahead and test our formula, plug in the values, and see if we get that. All right. So let's go on to the next one. First, we'll do Earth, and then we'll see what it is going to be on the moon. So here I put in our constant. Gravitational constant value is 6.67 times 10 to the negative 11 Newton meters squared per kilogram. It's supposed to be per kilogram squared. Okay. All right. So we have our values. Earth's radius is approximately 6.37 times 10 to the negative 6 meters. And Earth's mass is approximately 5.97 times 10 to the 24 kilograms. Right. Here we have our formula for the acceleration of gravity on the surface of Earth. It's a generalized formula. Now we go ahead and plug in our values. So G is equal to 6.7 times 10 to the negative 11 Newton meters. Those are units for that squared, divided by kilogram squared. And M, the mass of the Earth, is 5.9 times 10 to the negative 24 kilograms. And R is 6.37 times 10 to the 6 meters. Right? R is the distance from the center of the planet to the surface. And we square that. When you calculate the numbers, you plug it in the calculator, indeed, we do get the well-known value of approximately 9.81 meters per second squared. So that's acceleration of gravity. And again, please remember, looking at a formula here, it doesn't matter what the mass is of whatever is on the surface. It could be a person, a plane, it doesn't matter, right? You're still going to get the same value because that is not part of the equation. That doesn't factor in. Okay. Now let's test it one more time. Let's do one more. Let's test it on, let's for fun, let's calculate the acceleration of gravity on the moon, right? So let's go ahead and take a look. And again, we're going to use the same formula that we derived a second ago, right? This time, M1 represents the moon, and R represents the radius of the moon, okay? So our values, again, the gravitational constant doesn't change. It's still 6.67 times 10 to the negative 11, units that it has. This time, however, we have the moon's radius is approximately 1.74 times 10 to the negative 6 meters, and the mass of the moon is approximately 7.35 times 10 to the negative, I'm sorry, 10 to the 22nd 22 kilograms. We go ahead and plug those values into our formula, right? So G is a 6.67 times the mass of the moon, 7.35 times its explanation, and then divided by the radius squared. So the radius is approximately 1.74 times 10 to the 6 meters, right? We go ahead and calculate that, and we come up with a value of what acceleration of gravity on the moon. It's wow. It's almost a tenth, almost a tenth of the acceleration of gravity on the planet Earth. It's 1.62 meters per second squared. So if you fall on the moon, you're gonna fall at a much smaller rate, a much slower rate. Okay. So I hope that helped. It cleared up some things. I wanted to get a little deeper into it because in the book they spoke about it, but they didn't do like specific mathematical operations. They did say that they weren't going to get too much into calculation, but I thought I wanted to get a little deeper and show how we can use those laws that Newton determined or observed and come up with even, some well-known quantities that of motion. Okay, so hope you guys enjoy this. If you do, please like and subscribe, and I will see you in the next video. Have a wonderful day.